In this video cast, we'll take a look at a scale for acids and basicity of substances, and we'll take a look at how strong acids and bases can be calculated on this scale of acidity or basicity. There are four equations that govern the relationship between H plus concentration, OH minus concentration, pH, and POH. Make sure you have your notes out to write these down, and make sure that you have a calculator handy, because I'm going to want you to try your calculator as you learn how to do these relationships. The first equation is one we learned last video cast, where the concentration of H plus or H3O plus times the concentration of OH minus is equal to Kw, which is 1 times 10 to the negative 14th. This is true for any aqueous solution where there's water that gives us hydronium ions and hydroxide ions. The second equation comes from the definition of pH, which is the scale that allows us to rate how the acidity or basicity of something is. And the definition of pH, why did I write POH? pH is equal to the negative logarithm of the H3O plus ion concentration. Now I should take a minute here because some people get confused. Every once in a while you'll see me or someone write H plus, and then the next minute you'll see me or someone else write H3O plus. Those two mean the same thing. They mean the same thing. H3O plus, if you read it like this, called the hydronium ion, can be shortcut written by subtracting out a water and H2O, and then you just write it as H plus. So H plus and H3O plus mean the same thing. Usually there'll be like a little AQ down here below H plus to let you know that, hey, it's done in water, so there's a bunch of water molecules around that are actually glomming onto this H plus. So there's the second equation. pH is equal to the negative log of H3O plus. There are other P scales as well. And the other P scale that happens to be really valuable to us is the POH, which simply means we're going to take the negative log, not now of the H3O plus, but the negative log of the OH minus ion concentration. So you can see the difference here. One is the H plus and one is the OH minus. The last one is simply a derivation that you saw on the very first video cast, where you could take the negative logarithm of H3O plus and the negative log of OH minus, add those together, and they equal a number. And since the negative log of each of those is actually equal to a P scale, we can say pH plus POH is equal to 14. If you want to see a deeper derivation of this, once again, go back to the first video cast and watch it on the slideshow. So those four equations are the main ones we're going to use today when we do our calculations along the way. Make sure you have your calculator up for the next section. Calculate the pH, POH, OH minus for a solution who has an H plus, remember that's the same as H3O plus, of 1 times 10 to the negative fifth. Okay? To find the pH, we simply take the negative logarithm of this number, 1 times 10 to the negative fifth. So if you can't do this in your head, here's how to do it on your calculator. Take your calculator and type in the negative sign, and then after that type in log, so find the LOG button, and then put in 1, enter exponent to the negative fifth power, and you don't have to put the ending parentheses on there, it'll still work, and then hit enter. And since the logarithm is actually the exponent, we're just going to find out that it's equal to 5, because we took the negative of the negative exponent. And so the answer to the pH is 5 for if the H plus ion concentration is 1 times 10 to the negative fifth. And that's a good way to actually guesstimate to see if you're doing it correctly, is to take a look at the exponent and see if your pH is pretty close to it. If it's not within a value of plus or minus 1, you know you did something wrong. And there'll be a second or an alternate video cast where I can teach you how to do a lot of these logarithms in your head and come up with a pretty good approximation of what they are. Okay, we can use this next equation, pH plus POH, the one we just learned above, is equal to 14 to find out what the POH is. So if I know the pH is equal to 5, I can figure out the POH just by taking 14 minus 5. And it turns out that the POH is equal to 9. And then lastly, it wanted us to find the OH minus ion concentration. And the easy way to do that is to do the backwards log, or some people call it the inverse log. or some people call it the anti-log, which means that we are going to use the 10 to the x key on your calculator, and what you're actually going to do is take this POH to find the OH minus ion concentration and type in 10 to the x and then type in negative sign 9. So on your calculator, if you want to follow along with yours, type in the 10 to the x key. So on mine it's second, and then this key right down here, 10 to the x, it's right above the log. So it puts this sign on there, 10 to the x, and then type in the negative of the POH, which is 9, and you don't have to put the last parenthesis in there if you want, and you find out that is 1 times 10 to the negative 9th. And you can write it either way. You can write it as 1e negative 9, or you can write it as 1 times 10 to the negative 9th. Either one's acceptable in the AP exam. This is probably a little bit more correct mathematically, but you decide. Let's go on to one that's a little bit more difficult. Let's take a look at this one right here, the third one down, where it says calculate the pH, POH, H plus for a solution whose OH minus concentration is 3.5 times 10 to the negative 9th. Now there's a couple different ways to go about doing this. I'm going to give you one way, and I'll kind of describe to you the other way in case you want to do it as well. The first thing I'm going to do is take the negative logarithm of that OH minus ion concentration. And if I take the negative log of that, I'm going to have what's called the POH. So negative log of 3.5 times 10 to the negative 9th. I'll probably need my calculator to do it, although watch the alternative video cast in a little while and I'll show you how to do that. So type in negative, do it without a calculator, negative log of 3.5, enter exponent, negative 9th. Okay, hit enter, and it turns out that it's 8.45. We're going to round it to 8.46 just to be fun. Okay, 8.46 is our POH. Now, if you remember from last problem, we have an equation that is pH plus POH is equal to 14. Well, hey, I know my POH right up here is 8.46, so plug that number in here, 8.46, subtract it from 14, and I end up with a pH equal to 5.54. Lastly, I want to find the H plus ion concentration. Now there's two ways to do this. I'm going to do it one way, I'm going to tell you another way too. We could do it like we did above, where we take the 10 to the x key and we put in the negative pH, 5.54, or what we could use is the equation we learned last video cast. H plus times OH minus is equal to KW, 1 times 10 to the negative 14th. And if you take the OH minus ion concentration that they give us right here and plug that in, now we only have one variable to look for. So let's do it this way this time, where now I'll divide by the OH minus ion concentration on both sides, and I'll have solved for H plus. So on your calculator, type in 1, enter exponent, negative 14, and then divide by the OH minus ion concentration that they give us, 3.5, enter exponent, negative 9. And we end up with a H plus ion concentration of 2.85 times 10 to the negative 6th. 2.85 times 10 to the negative 6th is equal to our H plus, or H3O plus ion concentration. Lots more problems like this in here that you could try. The answers are actually in the book if you want to take a look at them underneath their sample problems. Next, write the dissociation equation for strong acids, hydrochloric, chloric, and sulfuric acids. We'll do a couple of them. Let's start with hydrochloric. The dissociation equation for that, when an acid reacts with water, is to say that the acid will give its proton away to water, and water will act as a base, and it will form H3O plus, and it will form the conjugate base of hydrochloric acid, Cl minus. Notice I only used a single arrow, and there's a question about that in just a little while. The reason why is because it's a strong acid, and our equilibrium will lie far to the right, and there will be lots and lots of this, and very little of these things remaining at all. Okay, secondly, let's do sulfuric acid, because this one's really interesting. Sulfuric acid, remember, is H2SO4. And if you remember from past video casts, this is called a polyprotic acid, meaning that there's more than one proton. There's two of them here. And it asks for the dissociation equations, so we'll actually write just the first dissociation of H2SO4 and talk about the second. Now remember, it's going to give up a hydrogen atom to H2O, so it'll form H3O plus, and then what's left over is HSO4 minus. And notice it's a single arrow because this is a strong acid, so it will completely dissociate. And notice whatever the concentration of these acids were, since it's all gone now, or at least pretty much all gone, has become this stuff over here. And the important concept to get out of this is not only to be able to write the equation, but whatever the molarity of these guys are, that's going to be the molarity of these guys. And now we can take the H3O plus concentrations and find things like the pH, the POH, the OH minus ion concentration, just like we did above. What happens to this, by the way, HSO4 minus? Remember, this is not one of the strong acids you memorized, but it is a weak acid because it does have an H that it could give away. Does have an H that it could give away. And so there'll actually be a second dissociation of this, HSO4 minus and water. It'll give another proton away, but this time you have to write two arrows because remember it's a weak acid, and it'll form H3O plus and some SO4 2 minus. So in the second dissociation, which would have a Ka2, we'd write it, this critter right here can still act acidic, although only weakly compared to the strong acids like these guys. So why is only a single arrow, not a double reversible arrow using the dissociation equations? And I think I alluded to that before. It's because these guys are strong acids, and you always use a single arrow with just a strong acid or a strong base to indicate that, hey, all of it, or nearly all of it, goes to form these products right here. If it's a weak acid, or a weak base, then you want to make sure to use this double arrow because actually the equilibrium is probably going to lay further to the left than it is to the right, or at least somewhere in between. Next, it says write the dissociation equations of some strong bases. Let's write barium hydroxide first. Barium hydroxide is BaOH2, okay? And when we dissociate this, remember it's an aqueous solution. It says we're going to dissolve these in water. It doesn't say that, but we're going to. And when we do these, it's common to just write them as aqueous like this, and then just draw an arrow showing them breaking up into their aqueous components. Since barium hydroxide is soluble and it is a strong electrolyte or a strong base, it's going to form Ba positive 2 and 2 OH minuses. Where did I get this 2 from? Well, it's because there's 2 hydroxides right here. So it's neat to notice that when you have the strong bases from the alkali earth metals, they're always going to give you double the amount of OH that you'd get from a strong base that's from the alkali metals, which is significant as well because OH minus can tell us a lot about a solution, because if we take the negative log of that, we can find the POH and then therefore the pH and the H plus ion concentration. So whatever the concentration of this critter is, remember it's all going to be turned into twice as much OH minus. So take a second right now and let's do potassium hydroxide and strontium hydroxide. Potassium hydroxide is easy. We're just going to write it with a single arrow and it's going to form K plus and OH minus, and I'm not going to put the aqueuses in there because we know that they're dissolved in water. Notice it's a 1-to-1 ratio here, so whatever the concentration of KOH is, that's going to be the concentration of OH minus. Strontium hydroxide goes back to the one that we just did with barium, where it's SrOH2, and remember this is going to be a single big arrow going this direction to give you Sr plus 2 and 2 OH minuses. Notice whatever the concentration of SrOH is, it's going to be double for the OH minus. Double for the OH minus. Okay? A couple of questions about pH, POH, and OH minus for strong bases and strong acids. Let's start with this one. Make sure you have your calculator out for this. Calculate the pH, POH, and H plus for a solution of 0.5 molar CaOH2. First thing to do is to recognize then when the strong base CaOH2 dissociates, it's going to give you a calcium ion and 2 hydroxide ions. So if you know that calcium hydroxide is 0.5 molar, how much OH are you going to have in the solution? Because remember, it's OH minus or H plus that drives what the pH or the POH is. Well, you notice it's a 1 to 2 ratio, so there's going to be twice as much. So technically, it's going to be 1 molar in OH minuses, or 1 molar of OH minus for the concentration. So when we calculate our POH, which is probably the logical step from here, we're going to take the negative log of the OH minus ion concentration. And since this is a strong base, all of it is going to dissociate and form OH minuses right here. And so we'll take the negative logarithm of 1. Hey, you might be able to do that one in your head. Log of 1 is always equal to 0. Hey, we're going to have a POH of 0. Is that legal? Yeah, as a matter of fact, it is. A lot of people think that the pH scale only goes from like 1 to 14. That's one of those fallacies that people told you a long time ago. It can actually have a negative pH or more than 14 for a pH. Same way with POH as well. To find the pH, then we'd take pH plus the POH equals to 14 equals 14. And if the POH is 0, of course, what is the pH? Well, the pH is 14 then, right? pH is equal to 14. Okay, and then lastly, it asked us to find the H plus ion concentration for this solution. And there's a couple different ways to do this, but I think the easiest way is, since you know the pH, you might not even have to type this into your calculator. Hit the 10 to the x key, and then type in the negative sign, and then 14. I can do that for you on the calculator so you can see it. Okay, 10 to the x key. If you look right here on the calculator, here's my 10 to the x key. So hit the second 10 to the x, see what it puts on there, and then type in the negative sign, and then put in 14, and hit enter, and voila, look at that, it's 1 times 10 to the negative 14th. 1 times 10 to the negative 14th, just about like this is written. 1e negative 14 is one way to write it. But remember that the pH and the POH is nothing other than the exponent, so if you know the exponent, hey, just tack it on to 1 times the, and you know what your concentration is. So this is the H plus ion concentration for this solution. Let's skip the next problem, and let's go on to this bottom one right here, because this is a little more confusing one, because it doesn't really have a strong acid or strong base equation like we wrote up above. It says calculate the pH, the POH, and the H plus for a solution that is 0.1 molar in O minus 2 from a salt such as Na2O. Well, when Na2O dissolves in water, it forms Na pluses and O minus 2s. Na pluses and O minus 2s. As a matter of fact, it's going to form 2 NAs. But as we know, Na is just going to be a spectator ion here, and then the O minus 2 is going to be the thing that's going to be very willing to accept protons. And so we're going to take the O minus 2 and we'll react it with the water solution that it dissolves into. We'll draw a single arrow here because it turns out this is a strong base. It's going to be a good acceptor of protons from water, and so we're going to end up with OH with a minus and OH with a minus right here, because this gave away a proton to this guy, and what's left over is the OH minus right here. So taking a look at the stoichiometry here now, for every one of these O minus 2s that you get rid of, every one of these O minus 2s that react, which happens to be 0.1 molar, how many OHs are you going to get? Notice there's 2 of them here. So you'll have to multiply your concentration by 2 for how many OHs there are. So it'll end up being 0.2 molar in OH minus. Now, if we know the OH minus concentration, my logical step is to take the negative logarithm of that OH minus ion concentration, and then you've got the POH. So following along with your calculator now, on your calculator, take the negative logarithm of 0.2. Negative log of 0.2 is 0.698, or let's just put, let's round it so it's easy. How about 0.7? So we end up with a POH of about 0.7. Okay. Now you can plug that into the calculator, into your head maybe. pH plus POH is equal to 14, and if the POH is 0.7, that means the pH has got to be 13.3. Is that basic? Oh yeah, very basic, right? pH scale, as a lot of people already knew, went from about 1 to 14. Actually, it can go a little above and below that too, but we have a highly basic solution here. And then lastly, if we wanted to find the H plus ion concentration, the easy way for me to do that is to say, I'm going to use the 10 to the x key and then put in negative 13.3, my concentration, or my pH value right here. Doing that on the calculator, again, if you want to watch me do it, is first hit the second button, and then hit the 10 to the x key right here, and then that puts 10 to the caret on there, and I'm going to put in the negative 13.3 and hit enter, and it turns out that it's 5.0 times 10 to the negative 14th, or 5 times 10 to the negative 14th if you want to try it on your calculator.